Kia ora everyone, welcome to this video which is going to take you through all of the basic calculations for strong acids and bases. This is a review for level 2 NCEA and it's revision if you're starting level 3 NCEA Aqueous. Let's start with a strong acid. A reminder that the strong acids are HCl, HNO3, H2SO4 and HBr. And a reminder that strong acids fully dissociate, as shown here for HCl. And this actually means that the concentration of the acid equals the concentration of hydronium ions. So if our hydrochloric acid was 0.112 moles per litre, we actually have an H3O plus concentration of 0.0112 moles per litre because the entire acid has dissociated. We now need to use pH equals negative log of H3O plus, and in this case we substitute the 0.112 in, so negative log of 0.112. And our answer comes out at 0.951. No units, 3 significant figures, and a reminder that we should check our answer to make sure it makes sense. 0.951 is a nice low pH for an acid, so that seems about right. Likewise for a strong base. Remember, strong bases are ionic, KOH and NaOH, the most common examples. These also, being strong, fully dissociate in water, as shown here. So again, we can make the assumption that the concentration of the base is in fact the same as the concentration of OH-. If we again assume that our concentration of NaOH is 0.112, that means we have an OH- concentration of 0.112 moles per litre. Unlike acids, there are 2 ways that we can calculate the pH if we know the OH- concentration. Let's look at the first way here. We can use the Kw expression. That tells us that the concentration of hydroxide multiplied by hydronium gives us the Kw, which we know is 1 times 10 to the power of negative 14. Therefore, rearranging this, 1 times 10 to the negative 14 divided by the OH gives us the hydronium ions. So 1 times 10 to the negative 14 divided by the hydroxide of 0.112 gives us a hydronium concentration of 8.93 times 10 to the negative 14 moles per litre. So now that we have our hydronium, we can negative log that as before to give us the pH. This time we get 13.0 to 3 sig figs, no units needed, and that looks like a reasonably decent number for a base. Let's look at the second way we can calculate the pH if we know the OH-, and that is to use this equation here. pH plus POH equals 14. So the first thing we actually need to do is calculate the POH, which comes from the negative log of the OH-. P actually just means negative log of. So if we negative log 0.112, we get 0.951. So this is our POH. And now if we rearrange the first equation, we can find the pH by subtracting our POH from 14. And in this case, as we would expect, we get exactly the same number of 13.0. Either way works really well. You just need to choose which way you're more comfortable with. The next thing we want to look at is how to calculate if we're given the pH and we're asked for the hydroxide and or the hydronium. The first thing we need to know is how to invert the equation, pH equals negative log H3O plus. The inversion looks like this. The concentration of hydronium equals 10 to the power of the negative pH. So a possible question could be to calculate the hydronium and the hydroxide for a solution if its pH is 8.24. The first thing we need to know is how to put this 10 to the power of the negative pH into our calculator. And the way that you do it is you push shift, then log, then negative, then the number of the pH. So shift log negative 8.24 gives us a hydronium ion concentration of 5.75 times 10 to the minus 9 moles per litre. If we then take our Kw and divide by 5.75 times 10 to the minus 9, we get 1.74 times 10 to the minus 6, our hydroxide concentration. Look at this pH, 8.24. It's basic, above 7, so we would expect our OH- to be greater than our H3O+. Let's just double check that every time to make sure our numbers look reasonable, and in this case, they do. Lastly, here are a couple of example calculations for you to practice. Firstly, with acids. Pause the video now and go back and see if you can calculate these, given some of the techniques we have gone through in this video. Okay, checking those answers now. Answer to question 1 is pH 1.47. 0.0341 is quite a high concentration for an acid, so that seems reasonable. Question 2, the pH is 1.61 and the OH- is 4.12 times 10 to the negative 13. Don't forget your units here, moles per litre. Again, those answers look about right as the solution is acidic. And now for base practice. Have a look at these two questions, pause the video at the end, and see if you can answer them both. Really quiet. Okay, let's take a look at those answers now. The answer to the first question, calculate the pH of a basic solution, ends up being 10.5, a reasonable answer for a base. The second question asked us to calculate both the hydronium and the hydroxide. Remember, it's a basic solution, so we'd expect the OH- to be greater than the H3O+. In this case, it is. Don't forget 3 sig figs and your units. Right, let's just take a last look at the equations you can choose to use. You have to actually keep working at it, and you have to figure out which way you like the best. I tend to like to employ a combination of both types, depending on the question. These equations and calculations can seem really difficult, but it just takes a little bit of effort, and then that makes a huge difference to your understanding. So I really encourage you to have a good go into doing all of the calculations for strong acids and strong bases. I promise you, you'll feel heaps better about it. Catch you later.